So one problem that I'd like to look at with you would be something like this. Now, the instructions for a problem like this would be to rationalize the denominator. Basically, we want to get rid of the square roots here. Now, the trick is to multiply by 1. You can't multiply both sides of this by some denominator or something like that because there is no both sides. There's no equation. But multiplying by 1 won't change the value of this, but depending on the form of 1, it'll change the way it looks. Does anyone remember the little trick here of what I want to multiply by in both the numerator and denominator? Reagan?
Square root of 3 over square root of 3.
Pretty close. We're going to have square root of 3 and square root of 3 in both of these.
4 minus.
Yeah. 4 and 4, and then you've got to change the sign. So that's going to be a minus in both the numerator and denominator. Effectively, you're multiplying by 1, something over itself. But the trick about this is you're multiplying conjugates. This is something in the form a plus b times a minus b. And when you multiply those out, some nice stuff happens. So I'm going to keep this together in the numerator, 26 times 4 minus the square root of 3. And let's see what happens in the denominator. I'm going to get 16 minus 4 square roots of 3, right, because of the outside terms. How about the inside terms? What's that going to give me?
4 times square root of 3.
Plus 4 square roots of 3. And then square root of 3 times negative square root of 3 is going to negative square root of 9. So, okay. The numerator, again, I'm going to leave alone for just another minute. But the denominator is going to simplify pretty nicely. And the denominator simplifies because the middle terms cancel each other out. I hope you can see that. Let me try and help out in that regard. These two terms disappear. How about the square root of 9? What does that give me? So what I end up with is 13 in the denominator. And maybe now you can see why I waited just a little bit to multiply in the numerator. Is there something you would suggest I do before I multiply in the numerator?
Reduce.
Yeah. At this point, you can cancel the 13 into the 26, and it's going to go twice. 2 times 4 minus the square root of 3. And that's fine for our final answer. If you want to distribute that and get 8 minus 2 square roots of 3, that's okay as well. But this is a good problem. I like that one. All right? I mean, it's not the funnest one. I won't lie to you. No one likes working with square roots, and rationalizing a denominator seems like a kind of a pain, but it is something we have to deal with. Questions on that one first? Let's take a look at a few exponential and logarithmic equations. So let me go back.
What section was this one again?
That was problem number 74. You know, as far as what section that would be, I'm guessing it's in chapter 9 someplace. Yeah.
You're a genius.
All right. Let's see here. Let's see. 55. 53. Let's start with problem 53. This is an exponential equation. And the interesting thing for your point of view, and mine really, is that I've changed the way I teach these over the years. There's actually a couple ways you can do this particular problem, but I've come around to one way that I just really like, and I don't really bother with the other way too much. So this is an exponential equation. You want to get the variable out of the exponent. The thing that gets them out of the exponent is the logarithm, because of the properties of logarithms. You know, that's something, again, that you should be expecting. Now I can just take log on both sides, and that's fine. But there's something that makes your life a little bit easier when you take the logs here. What would that be? Does Does anyone know? What could I do better about taking logs on both sides?
Taking the log base 2 to cancel out the 2.
Yes, perfect. So what's going on right now is that I'm really taking log base 10. Because I didn't write anything, so it's understood to be a 10. But if I take log base 2, then on the left-hand side, log base 2 of 2 to some power, those operations cancel each other out. I get x squared minus 2x. As a reminder, on the right-hand side, your calculator can do this. So can Desmos, although you have to work a little bit harder in Desmos to get this. So let me clear this out, and then you can kind of watch and remind yourself how to find log of a certain base. So the way I like to go to it is hit the math key, then go up. There you go, to A. So you can also hit alpha and then A as well. That'll take you there. But log base, oh, that gives me log base 2 of 8. Now, let's remind ourselves what this is. When you take the log of something, it's saying, well, what power of the base gives me this number here? What power of 2 gives me 8? 3. Now, the good thing is that if you don't remember that, or if it's a test and you're in a panic, hey, you've got it right there, all right? Although some of these you should be able to remember, but hey, this is a no judgment zone. As long as you can come up with a 3 here, that's great. Now, x squared minus 2x minus 3. Here's some practice factoring. Anyone got this? X and an x. Has to be a plus and a minus. And not too many possibilities here. A 1 and a 3. What solutions does that give me then for this problem?
-1.
-1 and 3.
Yep. Perfect. Thank you, ladies. All right. So there's one right there. Comments or thoughts on that one? Doing okay? Let's try another one. I kind of like this one a lot. And actually, you know what? We'll do it this way. So all I asked in this problem was to have you calculate the expression 3 log of 5 over log of 5 minus 2 log of 3. Now, I've experimented with this a lot in the past. I'm not going to take the time to do it now, but when I ask people to calculate this value, it's a train wreck. It's just a real dumpster fire. Probably because it takes a fair amount of finesse to put that into your calculator correctly. You have to use parentheses and whatnot. But tell you what, we're going to make this easier for you to put into your calculator this way. We're going to use the properties of logs. So again, this is more practice for you for your exam. Now, for instance, here I can use a property of logs that we usually use in the other direction. Instead of taking something here and putting it out front, I can put that up in the numerator. So, okay, in the numerator, or I said numerator, we're going to put that up in the exponent. So it's going to be log of 5 cubed. In the denominator, I'll do likewise with the 2. So it's going to be log of 3 squared. Okay, that's looking better. Then what? Well, I happen to know that 5 times 5 is 25, times 5 again gives me 125. So this is really log of 125. And that looks a little bit nicer in the numerator. Log of 5 minus log of 9 in the denominator. And there's one more property I'm going to use before I try and calculate this thing. Does anyone know what other property I can use? It's a property of logarithms. Give you a hint, it's in the denominator. Yeah, the division one. So this is the log of 5 over 9. That's a lot friendlier expression to calculate than what we started out with. You don't need quite as much finesse to get that. Now, could you have gotten it the right way originally? Absolutely. Nothing wrong with that. But when I ask people to calculate this versus this, the success rate is a lot higher with the one down below. So let's do the one down below. So it's going to be log of 125, parenthesis, you got to close off the log, divided by log of 5 divided by 9, parenthesis. Bam. So negative 8.4214, etc. Nice. Nice. Okay. Let's keep going unless there's comments or thoughts on that one. You can actually double check that works. If you were to store that value, say in x, you could check that it worked in the original problem by doing 5 to the x minus 3 and compare it to 3 to the 2x. So here's what that would look like. So I want 5 to the parentheses x minus 3, and maybe I didn't need the parentheses there, versus, did I get this equation right? Yeah, 3 to the 2x. 3 raised to the 2x. And notice you get the same decimal value both times. So it's nice that you can prove that you got it right. That's not necessarily part of the problem. You don't have to do that last part. Let's start with problem 55. Or let's continue with problem 55, I should say. So it's a log of 3 minus 2x equals, minus minus the log of x plus 24. Equals 0. Okay, well, this one actually could be done in a couple different ways, but let's do it the easiest way. And the way that I kind of want to demonstrate things is I'm going to move that term to the right-hand side. And when I do, I get the log of 3 minus 2x equals the log of x plus 24. And that's perfect. If I have the log of something equals the log of something else, then those two somethings here and here have to be equal. So basically I can get rid of the logs and just write, 3 minus 2x equals x plus 2. Let's add 2x to both sides. I get 3 equals 3x plus 2. Subtract 2, I get 1 equals 3x. 1/3 is x. So yay. Oh, you know what? I was just looking back at that. That should have been a 24, 24, 24, 24. I was like, wait a minute, that doesn't look like it checks. Because the next thing I was doing is I was kind of doing a mental mind check here. I want to make sure that that fits in the original problem. So yeah, thank you. So let's see, it's going to be 3x. Let me go back to here. So that part's okay. 3x 4. Yeah, so this is going to be subtract 24 from both sides. We get negative 21 equals 3x. There we go. And I think I know why I like this problem a little bit, is that a lot of times people want to throw out a negative answer. A negative answer is not the problem. The problem is taking the log of a negative number. So let's take a look and see what happens if I were to try and substitute this back in here. If I was trying to substitute this back in, negative 7 plus 24, does that give me a negative number? No, it gives you 17. We're okay there. 3 times negative 2 times negative 7. Well, negative 2 times negative 7 is going to be positive 14 plus 3 is 17. So it works in both of those. It doesn't give you a negative number in either one. In fact, you get the log of 17 minus the log of 17 is 0. So that it just works. The big thing is is not worrying about a negative number, it's worrying about taking the log of a negative number. That's where you run into problems. Okay, nice one. So that's one way you can solve logarithmic equations. But it doesn't always work out that way for us. So let's take a look at problem 56. A little different spin on this kind of stuff. So in problem 56, it's log of x squared equals 2. All right. 56. What base logarithm is understood to be here? What base is understood but not actually written? 10. It's understood to be base 10. Now, unlike the last problem I had the log of something equals the log of something else. I don't have logs everywhere here, do I? I can't do it with the last method. It just isn't working here. But what I can do is I can rewrite it. And one of the things that I would star at the top of your test when you get it is I'd write down this. Log base A of x equals y is equivalent to, that's what I mean by this bidirectional arrow, is equivalent to a to the y power equals x. That's the thing we got going here for ourselves. So what would that be as an exponential equation?
Would it be 10 squared equals x squared?
Yep. 10 squared equals x squared. So 10 to the second power equals x squared. Or, better yet, 100 equals x squared. And here's the tricky part.
10.
If you just give me 10, you're going to lose a point or 2. Oops. Why?
Should be plus or minus.
Yeah, this is a quadratic equation. There's a positive and a negative solution. So it should be plus or minus the square root here, plus or minus 10 equals x. Yay. Now both solutions check. If I put in 10 and square it, I get 100. Log of that's 2. If I put in negative 10 and square it, I still get 100. And the log of 100 is 2. So it checks. Now let's take a look at problem 57 here. We solved logarithmic equations by 2 different methods. The first one was when you had the log of something, it was the log of something else, and we got rid of the logs. The second one was by rewriting it, like in problem 56. Which method are we going to use for problem 57, which is the log of x plus the log of x minus 48 equals 2? Are we going to use this method, rewrite it, or are we going to use this method where you have the logs and we canceled out the logs?
56.
It's going to have to be 56. Thank you, Reagan. Can someone tell me why? Why does it have to be the second method?
Because they all don't have
Excellent. Thank you, Michaela. They all don't have a log. All right? This 2 doesn't have a log in it. Now, before we do this trick, you've got to get that log term together. So I can do that with the product rule. It's going to be the log of x times x minus 48 equals 2. That's your product rule. You're bringing those terms together as a product and taking the log of the product. Let me rewrite that one more time by distributing that. X squared minus 48x. Let's go back and remind ourselves of something. Gavin, what base is understood to be here?
10.
10. Excellent. Can you rewrite that using exponents for us, just like we did in 56? What to what power equals what?
10 to the second power equals x squared minus 48x.
Perfect. 10 to the second power equals x squared minus 48x. So that's 100 equals x squared minus 48x. Let me put that 100 on the other side. And when I do, it changes signs. And now I got to factor it. And I'll help you out with the factorization. It's x minus 50 and x plus 2. So that gives me two solutions, right? X equals what, or x equals what?
X equals 50 and x equals negative 2.
Excellent. Now 50 works out okay. If you're to check it, it's not going to give you the log of a negative number. Here you get log of 50, here you get log of 2. But what about this one? That's extraneous. You've got to get rid of that one. Because you can't take the log of a negative number. Period. End of story. So there's some quick review on logs for you. I would definitely expect a couple problems or two for logs. This kind of stuff in particular could be some easy questions. I could give you something quite short and simple like, let's see here. Log base 6 of 7,776. I think that's 5. So the question would be, what would it be like using exponents? Well, we've kind of already done that a couple times here in 56 and 57. But
6 to the 5th power equals 7,776.
Excellent. 6 to the 5th power equals 7776. Nice. I could also start out with something over here, like 2 to the, I don't know, let me think of something big. 2 to the 12th power equals 4,096. How would you write that using logs? So that's going the other way. Here we start out with exponentials. Log base A of x equals y, a to the y equals x. Somebody started to tell me.
Log base 2 of 4,096 equals 12.
Log base 2 of 4,096 equals 12. Perfect. So a couple quickie points. If you remember this relationship right here in the middle, those are some quick points you can get on the exam. Synthetic division. I forgot to test you on the last exam on synthetic division. My bad. I apologize. I hope you weren't offended. All right. But let's say x cubed minus 5x plus 7x, or x cubed minus 5x squared plus 7x minus 3 divided by x minus 2. I want this done synthetically, not by long division. You can use synthetic division when you're divided by x plus a number or x minus a number. So it's actually going to work here. So lots of little quick partial credits that you can get on this kind of thing. First of all, what number is going to go out in front?
2.
2. Nice. 2. Excellent. And how about somebody on Zoom here? What number should I put underneath here?
1, -5, 7, -3.
Thank you, Joe. Nice. So let's think. Even though it's not written, a lot of times I put a 0 there just to remind ourselves. Now you add to go down and multiply to go up. So that's going to be a 1. 2 times 1 gives me 2. Add going down, I get negative 3. 2 times negative 3 gives me negative 6. Add going down, 7 and negative 6 gives me 1. 2 times 1 gives me 2. Add going down gives me negative 1. Now please don't leave it like this. I get stuff like this all the time, and you're going to get 2 points out of 5. There's a quotient and a remainder that you got to interpret. Tell me what these mean. Pause the video if you are watching this later, but figure out what this means. Now I'll give you a reminder. It always starts out with this is their constant, that's a coefficient of x, that's a coefficient of x squared. And if I had more, they'd keep on going this way. What's this negative 1 about? Yeah, that's the remainder. So during the month of December, I call it the reindeer, but anyways, it's for right now, it's the remainder. So our answer is going to be x squared minus 3x plus 1 plus negative 1 over x minus 2. You could also write it as x squared minus 3x plus 1 minus 1 over x minus 2. Either one is fine. I have no preference for one or the other, whatever is easiest for you. From the last exam, let me see if I can't pull that one out. Yeah, here we go. There's two different things that are easy to confuse, and I think they did get confused for a few of you. Yeah. Problem number 6. This is your augmented matrix right here. So all it is just kind of wrapping your system of equations with that matrix notation, putting a little bar where the equal sign is, but that's your augmented matrix. In contrast, if I wanted to write this and solve this as a system of equations with matrices, A, B, and X, A is the matrix of your coefficients, B is the right-hand side, and X is kind of your variable. Now, you're right that X is kind of doing double duty here, but you know, it is what it is. Let's take a look at how you can solve a system of equations on your graphing calculator with that idea. Now, take a look at all the writing I did here. It's a fair amount of work, right, to do this one. But a cool trick moving forward for you to know, not that you're always going to be able to use it, but you know, cool and you should know, is being able to solve this with a matrix system of equations. Now, there's two things that we're going to need. We're going to need A, which is going to be the matrix of our coefficients. So 5, 2, 3, 4, 2, negative 3, 3, 1, and 1. And then B is going to be the right-hand side. So 14, 5, and 8. Okay, let's put those into our calculator and see what we can come up with. So let me clear out the stuff. To put that into your calculator, you want to go to the matrices. So you're going to hit the second button and then the X inverse key. You can keep track of my keystrokes down here. I want to edit matrix A. So I'll just go to the left. You can go 2 to the right or 1 to the left. Press enter. The size of my matrix is going to be 3 rows and 3 columns. Bonus points. Who remembers my corporate sponsor for this stuff? RC Cola. Yeah, it's rows and then columns because it's always number of rows and then number of columns. So where is it? Let's see. RC Cola. Yeah, my corporate sponsor for that stuff. Yay. Anyways, matrices is always rows, then columns. A couple years ago, one of my students bought a 24-pack of RC Cola and passed it out. It was kind of fun. So, in any case, let's see here. I want to calculate A inverse B, but I got to type in the matrices first. This is going to be a 3-row and 3-column matrix. So I want to type in a 5, a 2, 3, 4, 2, -3. Make sure you use the negative key on the bottom of your calculator, not the subtraction key. And then 3, 1, and 1. When you're done with that, exit out of here. Quit. We got to enter another matrix. So I'll just quit and do this again. I'm going to clear this out. So one more time. Second matrix. This time, go over to edit, but down to B. We want to edit the second matrix. And it's a good thing you remember RC Cola, because that'll tell you the size of this matrix. What's the size of that matrix?
1 by 3. No,
How many rows, how many columns? Start with the number of rows.
3 by 1.
3 by 1. Perfect. It's a 3 by 1. If you enter a 1 by 3, it's not going to like it. Or at least it won't like it when it comes time to multiplying. So it's going to be 14, 5, and 8. Nice. And that's it. Those are the two matrices that you needed to enter. To get my solution, all I need to do is do A inverse times B. So second matrix, here's matrix A. Click the inverse key, and then do second matrix, and then I'll type the number 2 to get matrix B. A inverse B, that's my answer right there. Ooh, pretty cool. Pretty cool. Very nice. Now, there's a lot more to matrices and working with them that we'll cover in the next class. But at least now you've got an idea of what I was looking for in terms of problems 5 and 6 and the applications of it. I mean, it's kind of nice. You can write something as a matrix system of equations and solve it. Although if you tried to solve this one that way, it would say non-singular matrix. And that's because these two lines are essentially the same. I think I used those, yeah, in problem number 3 here. Did anyone notice that? I used it twice. Actually 3 times, really. 1, 2, and 3. So, but these two lines are essentially the same. If you multiply the bottom equation by 3, you get the top equation. So it's a dependent system. It's a consistent system if what happens? What has to happen if your system is consistent?
They have to meet.
Yeah, they have to meet. So this is a graph of a system of equations. It's going to be consistent if the lines meet. Well, the only way the lines won't meet is if they're parallel. So these are clearly not parallel. Even though it doesn't show the point of intersection, they have to meet because they're not parallel. So this is going to be consistent. And it's independent because the lines are different lines. So yay. Boy, I'd like to spend a lot more time on this than we've got. Let's see. Other things, consistent, dependent. Graphing a parabola. You've got some things with parabola on them. We've worked with those. I'm trying to think what test that would be. Maybe the second test or the third test. Let's go for it this way. Table of contents. Exam keys and handouts. Here we go, exam keys. Exam 2. Nope, maybe exam 3. Yeah, here we go. So find the x and y intercepts, find the vertex, and the equation of the axis of symmetry. Those are all good questions. So the vertex, you can get that especially from the first form of the equation that I gave you here. Let me get back to that and zoom in a little bit. Yeah, right here. Start by making the squared term equal to 0. What value of x makes the squared term equal to 0? 1. If you put in a 1, this term turns to 0, and then you get y is negative 8. So 1 for x gives you negative 8 for y. You can just read that off. If you set x equal to 0, that gives you the y-intercept. So between those two ideas right there, that's a quick 3 or 4 points. If you set y equal to 0, that's a little bit more work in solving, but I gave you 2 different forms of this equation so that you could use either the square root property, or you could use a quadratic formula or factoring. You know, whatever worked for you. There's really a lot of different ways you could have solved the equation, problem number 9, to find the roots. So let's take kind of a quick look at that, and then I'll finish up with the Pythagorean Theorem, a quick reminder on that. So we've got y equals 2 times x minus 1 squared minus 8 equals 2 times x squared minus 4x minus 6. So a couple different ways you could solve this one, and it's kind of up to you. So what you're interested in right now is setting y equal to 0 to find the x-intercepts. So if I do that here, 2 times x minus 1 squared minus 8, then what I would do, because this is a squared term already, I move the 8 to the other side, divide both sides by 2, and then take the square root. So plus or minus the square root of 4 equals x minus 1. And it's really easy to get kind of led astray here because of that plus or minus. People want to move the 1 over and go, oh, plus or minus 1. It's not quite that simple. So let's take just an extra moment and do the positive case. That is assuming we have a positive 2. And the negative case, assuming that they have a negative 2. If I add 1 to both sides, I get x equal 3. If I add 1 to both sides here, I get x equal negative 1. Cool. Now in comparison, if you wanted to, you could say that, okay, you know, I'm going to use this form of the equation. I don't like the other form. I'm not a big fan of the square root property. That's fine. And your choices at that point would be either factor it, or what else? What's your ace in the hole for solving quadratic equations? Quadratic formula. You could use a quadratic formula right here. It would work. Kind of be a lot of work, but I mean, I'll write it down just for you guys to have it. This is probably another really good thing to know for the final exam, and expect something, at least one problem with imaginary roots. But
Can we do something with like the distance formula?
we did do the distance formula, and midpoint formula. I'll write those down after we finish this problem. Those are both good to know. But for my money, factoring is the best thing to do. Does anyone notice anything convenient about this up here?
You could factor it.
How?
Does it factor out?
Yeah, 2 factors out, which leave behind x squared minus 2x minus 3. And now we can kind of ignore the 2. I mean, sometimes I take the time to divide it out, sometimes I don't. And I think we've dealt with this one before here this morning. You've got something times something times something equals 0. Well, 2 can't equal 0, so I'm not getting a solution from that first part. But where does x minus 3 equal 0? When x equals 3 or negative 1. So, of these methods, factoring, I think, works the best. But it's up to you, what you would think. Couple remaining problems here. Somebody asked me about the distance formula. Yeah, that's good to know. Distance would be d equals square root of x2 minus x1 squared plus y2 minus y1 squared. The big problem I get with the distance formula is people want to put a minus here all the time. A lot of times people give me the square root of a negative number for the distance. You will not have an imaginary distance for these problems. If somebody could mute themselves, that'd be great. Let me see. There we go. Thank you. The midpoint formula is going to be x1 plus x2 over 2 and y1 plus y2 over 2. Basically, you're averaging your 2 points. And since I'm on this kick here, let's do the slope. Slope is m is y2 minus y1 over x2 minus x1. So notice the midpoint formula is kind of unique in this in 2 ways. One, instead of subtracting x1 and x2 or y1 and y2, you're adding them and dividing by 2. The other thing is that you're actually getting 2 answers here, the x coordinate and the y coordinate, whereas these are each just one number. And the Pythagorean Theorem. Does anyone remember that? Excellent. A squared plus b squared equals c squared. That's for a triangle that looks like this. A, B, and C, where C is your hypotenuse. So you might see a problem about a handsome athletic mathematician who goes skiing, but that's just a hypothetical person. All right. Comments or questions? All right. Let me give this one a rest. Oh, one last comment. Something that everyone really struggles with, and it's, I don't think it's fun for either of us, but it is something that I would suggest you're comfortable with, and that'd be factoring. If you look back, let's see here, table of contents, final exam review. There should be a whole page of factoring problems. Yeah, right here. So let me kind of zoom out on this a little bit. 4 terms, factor by grouping. This one is the difference of squares twice. First one and then the second one. Here, factor out the GCF. This is one of those ugly ones where the way we did it in class is you multiply the outside numbers. 8 times 15 is 120. Look for 2 numbers that multiply to 120 and add to 22. I'm trying to think what those would be. 2 numbers that multiply to 120 and add to 22. It wouldn't be prime.
Oh, yeah.
10 and 12. Yeah, 10 and 12. There you go. Perfect. This one is prime. How come this one's prime?
Because it's adding rather than subtracting.
Yeah, it's the sum of squares. So up here I had the difference of squares. That you can factor sum of squares is prime. This one you factor out the negative and then work with it. This one, anyone have any idea of what to do with this one? Let's write that one down. Y cubed, or 125 y cubed minus 27 z cubed That's the difference of cubes. A cubed minus B cubed. A minus B, A squared plus AB plus B squared. It is not, and nor will you endear yourself to your professor, it is not 5y minus 3z cubed. It doesn't work that way. By the way, what's the word that we use to remember this? How this factors? There's a word that helps us remember the signs. Anyone remember? Soap. Same sign, opposite sign, always positive.
How does she remember this stuff?
She's good. She's good. So this would be 5y minus 3z, and then I want 5y times itself, right? Because I got to square this, so that's 25y squared. And then 3z times itself, that gives me 9z squared. And then the middle term is going to be 5y times 3z, which is going to be 15yz, plus and plus. All right. All right, so cool. Cool. Oh, there is one other one that was below that, x squared minus 16x plus 64. If I give you something like this, if you factor it like this, x minus 8 times x minus 8, you're going to get 2 points. Does anyone know what you got to do to get 3 points?
X minus 8 squared.
X minus 8 squared. Excellent. Good luck on the exam.